And then, sure. Okay. We also have the program counter here and an instruction register. You might notice right away that the instruction register and the PC, the program counter are 16-bit, and these guys are all 8-bit, and everything here. The reason for that is that the actual code memory is, all the instructions are 16-bit, and I think the address is 16-bit too, but the RAM is only, for main memory is only 8-bit, which is kind of weird. This is actually, I think, term, if I remember right, hardware architecture.
Yeah, if you have the separate code memory and data, yeah.
Yeah, that's what we have.
For instance, when it's in the von Neumanns at Princeton. Okay, and you have a big
Yeah.
address space for your code, which is good. And presumably you don't need that much data space for whatever you're doing. So.
No, yeah, theoretically you shouldn't.
And your registers, since your general purpose registers are all 8 bits, it makes sense to have memory data 8-bit also.
Yeah, right. I think there are probably ways I could have done this if I hadn't used fixed size instructions. That would have been easier, but I ended up using fixed size instructions, so I couldn't really find either way to not have that dilemma. But anyway, there's an ALU over here. I can go in a little bit in that. I'm not going to go too deep into that because we kind of already just talked a lot about things like that. And then the control unit, that one's fun.
It is best to have a fixed length of your instruction. I mean, having the fixed fields is another thing. Like if you have variable field lengths, like your opcode length is different, or your operand fields are variable, then it slows up the processing. But if you have the whole length is different, then that's a whole other mess for the instruction register to deal with.
Yeah. Okay. So yeah, so this is the control unit though, and you can see like it has a ton of outputs. Can you guys read any of these things on your screen?
No, I can. Yeah, I can.
Or
read
are they
it.
too blurry?
No, it's pretty clear. Let's see, is a high resolution imaging here? You have it. This is not YouTube. Oh, I was thinking you had YouTube. This is not a video. So yeah, it's the resolution's fine. I can see.
Okay, I just wanted to make sure you could read them. Yeah. Yeah, so these are all, the control unit takes in clock current instruction and flags, and everything it outputs are basically control signals that dictate to the rest of the machine what data is allowed to move and to where the data is allowed to move. And so that's this whole section over here on the left is the bus control. And so there's a lot of signals from the CPU here, this whole section all down here on the left for controlling what data is taken from where and where it's getting mapped to. Like over here we have on the very left, these two multiplexers are used for taking the registers and picking one of them to use as an operand for the ALU. But those also get forwarded through to other things too, because sometimes they're not just used for the ALU. The XS and YS tunnels here from the control unit are used to pick the actual those actually pick the actual operands for the ALU. And then X and Y get forwarded over on the right here into the ALU. And then you get A and B as an output. But even then, everything else is, we have a lot of things to switch over what actually goes where.
And A as your accumulator is, the B is the extra for multiplication and division.
Yep.
Yep. Okay.
Yeah, and I can go over.
Did you say F was your status register?
Yeah, that's for all the flags.
The flags, okay.
Yeah, so I can just go and show you the, actually I can do it from inside here, I forgot. Here we go. This was the ALU. I'm not gonna spend much time on this because I think we've all gotten the basic idea of how to do an ALU by now. I'm hoping anyway, unless anyone disagrees with me.
No, it looks good. Are you doing two's complement for your?
Yeah, I use two's complement. I did pull a few weird tricks in here. I couldn't find a more efficient way to do signed multiplication, but it works. Yeah, so this has just a few inputs and out. Yeah, X and Y for inputs, A and B for outputs. Takes in flags, spits out flags, and 4-bit opcode to determine which one we're actually doing. So you can see on the right-hand side here, well, down on the left here, actually, these are all the computations for all this that will determine, like the results of the operations. So addition, subtraction, multiplication, division, signed versions, logical operations, and shifts. And then up here on the right, we just pick which one we want for the results based on the opcode. And then these parts down here just go through the and pick which flag is actually going to be the flag that's used. So like FC, that's the carry flag. FO is the overflow. FZ is for whether or not the result was 0, and FS is for whether or not the result, well, this is for the sign of the result. 1 if it's negative, 0 if it's positive. Yeah. One thing that is worth noting in here is this is something I picked up last minute from the x86 assembly language, or from any of those, from those architectures, that you'll notice that I use the overflow flag for addition and subtraction. Normally, that's, you could use overflow for multiplication if your value ends up using more than 1 byte. You could also use that if for division if you end up with a divide by 0 error, which is what I've done here. But we also use it for addition and subtraction, and the reason is because over here, for addition and subtraction, this actually stores the result of unsigned addition and subtraction, well, for the carry bit, as where over here we reuse the overflow bit to indicate what the whether there was a carry for signed addition and subtraction. And that is utilized to actually do comparisons within the CPU to actually, so you could do subtraction and compare the result. And that's how you're able to tell something with less than, greater than, or equal to, or things like that. So anyway, that's the entirety. Any questions there? Anything? Okay. I can go back. So that was the ALU up here. The only other thing is this guy. So this is the CU, the control unit. Ethan and I kind of cheated our way through this. This was interesting. So this thing keeps track of the current phase of the machine instruction cycle. We only actually ended up using the first 2 phases, which is interesting. And it takes sense. So here you'll see the instruction, current instruction getting broken apart. We take the higher bit, or the higher byte is the opcode of the instruction, and then the lower byte is actually going to be various other details, which will either be one singular immediate value, which is directly part of the instruction, or it's going to be one of these two could be a register index, and those are 3 bits each, which leaves 2 bits unused. So anyway, so there's that.
When you say you're only using the fetch and decode, is that because everything just kind of flows as soon as you decode? All the pathways open, everything flows. So you're not like having a set stage where you bring things into queues, buffer them right outside the ALU, and then wait and have a whole finite state machine phase for like pushing.
Yeah, basically.
So you just kind of open all the pathways.
In physical practice, it might be better to have that split up.
You actually do need to if you were looking at timing traces, because you got to let the thing settle. If you just let everything flow, you can have weird race conditions. Like you don't want everything just coming in the ALU at different times, because you could be adding like something that was previously.
Yeah. That's what I'm hoping eventually. I mean, if we can get timing diagrams working, that's what I'm hoping to be able to learn more of, because right now it just kind of came together like this.
Well, this is what you've done here is the beginnings of what would be a whole semester project, or like a senior project almost. If you had the full timing diagrams and everything. So this is great.
Yeah.
Criticize it. Yeah.
So let's see. Over here on the right-hand side, I'm going to go over the stuff over here in this window on the right. So yeah, these are all the outputs from it, and so these are all going to be determined inside the control unit, and this happens large part thanks to this gigantic chunk of ROM here. This was the shortcut I took to, based on the amount of time I had, Ethan and I were able to do something more like, I'll explain in a moment, do this instead of having to write out all the circuits in Logisim. That was going to take a while. And also for purposes of manageability, that just wasn't going to be feasible to design the entire instruction set like that. This is also part of the reason why nothing ever got split into multiple phases. So yeah, each one of these is a 32-bit word. Ooh, I don't want to do that. Go back. These are all 32-bit words. And so when we designed this, we actually specified all this stuff in an Excel file, which I forgot I moved. Shoot, let me just renamed all these folders. Let me go find it. Open, browse, desktop, eTown, advanced computer engineering, lab, CU specs. There we go. Yeah, so this is how we designed all this. So in here you have all these instructions. On the very left-hand column is the mnemonic for the instruction, and then everything else after that is various information about what things to actually turn on and off and how to choose different things for data flow. So like this first one here determines the actual opcode that's used for the ALU, if any. These determine which what to actually use for the operands of the ALU. This determines what's going to get used as the input for the program counter, and this determines basically determines whether or not to actually change the program counter, so on for other things down here. So these actually control everything. So all these things here are actually picked right out of a 32-bit word from the programmable map unit here. That was our shortcut. But we specified all this in Excel, and then I discovered recently that I can use Python to process an Excel document and convert all of this into something else. So I did that and converted it into a file that Logisim can read.
Huh, that's cool.
And then you just right-click and you can just load the image in here. So that's how that got in here. So every time we ever needed to make a change or add an instruction, or in one case remove one because I accidentally created an invalid instruction. Thank you, Ethan, for catching that.
That's cool.
Yeah, we're able to easily fix that up. So yeah, Ethan caught a mistake I made when I was putting together part of the instruction set, where I had an instruction that was supposed to put a immediate value into a register, like a general register. But the problem you'll notice right here is, because of the way this is split up, you can only have an immediate value, or you can have a register or two registers. You can't have an immediate value and a register. That's not possible the way this is set up.
That's not abnormal. The 8051 didn't have those mixed addressing modes, and then the 8251 came out, and they tripled the size of the instruction set, basically because they were mixing all the different address modes for every instruction, and it made it unnecessarily complex in my opinion, for what's supposed to be a simple device. So
yeah,
I assume you're leaning towards more of a microcontroller kind of thing here than a full-blown processor.
Yeah, this is probably more of a microprocessor kind of thing. And actually, one of the ironies, I'll go back to this page. I'm going to go back here anyway now. Oh, also, I'll explain this first. And I'll get to the irony of what I was going to say. This also is just to control the, so for the program counter, this takes in values from the current flags register and determines, based on that and based on what you've selected from the programmable map from the current instruction, determines whether or not the program counter can be set. And so that can utilize information such as whether the carry flag was set or not. So like, and that lets us do things like jump if the carry flag is set, or don't jump, or jump for an equality or a non-equality, or less than or equal to, or
Right.
things like that.
That's good.
So we're able to control that through this part here.
Good.
Anyway, yeah, one of the ironies of this whole thing is that this has no method for handling input and output from the CPU. So basically, it can do compute. You can load the stuff into ROM for the program and then set it running, and it will just run, and that's all it will do. You can't do anything useful with it. It's just a pointless machine.
Well, it would be an embedded ASIC kind of thing, where you develop your code and your idea, and then you burn it in, and this is a way to visualize it. So it's not.
Yeah, you still have to be able to connect to other things. So that's the problem.
Well, the I/O. Well, yes. I mean, there are two things there. The I/O for inputting changeable code is one thing, which is not a problem if you're going to mass produce something that just has a fixed function. But the I/O is a whole other thing. And yeah, that would be something to work out. You typically do memory mapped I/O. So if you just treated it like memory addresses, right?
Yeah.
But then you still have to have control signals to.
Yeah, I looked into ways to do it, and there were so many ways to do it, but they were a little above me still right now. So I'd have to look into that more.
It's a little tricky. If you remember in 333 class, the input and output ports of the 251 microcontroller, there's different weird things you got to do there. You need input and output buffers, and then you need like pull up resistors and things to actually get the actual signals to work coming out. So to deal with the actual outside world, not that you would need that in a logic simulation, but it is a whole other level of, to do something like that. Yeah. So this is plenty this is just one of a series of labs. I mean, well, it's a couple labs, but
Yeah.
still this is.
See. So the other thing was Ethan and I both did this. Ethan wrote an assembler for this, which was really helpful. I ended up writing one eventually too, but his was definitely more helpful because we needed one pretty quickly, and he got us one fast. So, but yeah, so we have an assembler we can use for this, and I've even developed. So here's some example programs. Well, here's just for like this is like an ALU test I did. So I actually just threw together a quick plugin for Notepad++ to color code all this. So this is the idea of what the assembly would look like for this. So you can do things like, so the way this works, you have the mnemonic for the instruction in the beginning.
Okay.
And that's for everyone. This is followed by a set of operands. And if you have something like, for instance, a move instruction, which moves data around from one location in memory to another, we'll take a value to move, and then the destination on the other side of this arrow here.
That's interesting. So your syntax for your code's actually an arrow. That's not your register transfer notation. That's actually the syntax of your code, which is understand. I mean, it's logical to mix what.
Yeah, it helped distinguish between some weird things I did.
Yeah, no, that's very descriptive. I mean, that's nice when the syntax tells you what's going on.
Yeah, it's a little bit wordy, but it works. So you have like this is an immediate value here, and then that's being moved into the accumulator.
Yeah. And then I like the multiply because you can see that you're using the A and B there, which you need.
Yeah, and multiply. Yeah, you have A and A and 3 in this case, so they're added together, and then they're put into A and B.
Right, you hardly even need register transfer notation at all when you do your code makes sense. And your syntax code. Yeah.
This was a huge improvement for testing the machine.
I'm surprised more assembler doesn't actually look like that. I've never seen that.
It is a little wordy though. So, but we do other things. You'll notice for like subtraction, we actually have 2 versions of subtraction. There's a reason I did a test twice here, because in one version, so like every time I write A in the assembly code for the accumulator, what that's actually doing, we don't actually specify that as a register in the actual instruction. That's just implicit. It's essentially implicitly specified by the opcode itself. So it's just assumed to be there. But for that reason, there would be no way to distinguish between this version and this version, where you have the you're doing the accumulator minus an immediate value, or an immediate value minus the accumulator. So there's actually 2 separate opcodes for that, one of which takes the accumulator first and one of which has the accumulator second. And I had to do it this way. I use this notation because it allowed me to distinguish between them.
Well, that's interesting. So the actual mnemonic of sub, there's 2 different versions depending on the rest of the code that you write out. Yeah. Okay. Yeah. I mean, as long as the programmer understands that.
Yeah.
That's fine.
I have an entire document too, where I show all the syntax for everything and describe what every command does.
Wow. Do you plan on continuing all of this? I mean, is this going to be part of what you want? You're doing a whole different thing for yours.
Probably, but I mean, yeah, I was considering. I mean, this is like, I mean, I would probably redesign a lot of things in this, but like it was, it was interesting. Um,
And you and Ethan have worked closely enough together that if you continued, Ethan's stuff is fully understandable when he rides off into the sunset to Phoenix Contact.
yeah,
Or wherever you're at.
yeah.
That's cool. No, I'd like to see more of this again. Well, keep going. I mean, you show me more stuff.
Okay, I'll show you a little. Yeah, I also in the assembly, you can make numbers negative, and all that actually does in the assembly is, I mean, the compiler, the way the assembler is doing this or handling this kind of notation is that it's actually just every time it receives a negative sign followed immediately by an immediate value, it's actually taking directly in the assembler. It's doing this during compile time. It takes the immediate value and applies 2's complement to the binary form of it, which converts it into a negative form.
Right in the assembler. That's interesting. Yeah.
Yeah. So this is a shortcut. A lot of compilers will take shortcuts like that.
Yeah.
I actually, when I wrote my version of the assembler, I ended up I could not write mine as fast as Ethan did, so I used Antler, which is a compiler to write most of my compiler for me, and then finished from there on. So that made it easier to get this down quickly. But and there's also, you can write it in binary by ending the number with a B, uppercase or lowercase, and you can also do it in hex by ending it with a lowercase or uppercase h.
Yeah, that's like the 8051 microcontroller, right?
Yeah, I took some inspiration from the 8051.
Yeah, yeah.
Let's see. The other one, let's see, another good one was let's see. Well, here's a memory reference. So this is this will move an immediate value into A. If you can't move an immediate value directly into memory, you have to put it into the accumulator first.
Okay.
So this will move it into the accumulator, and then this will move the accumulator into a location in memory, which this time is specified by an immediate value. You could also do it by register value. So this will put it in the value 42 into memory location 6. This node is invalid now. We fixed this, but this would move something from my memory location back into the accumulator. And this was actually an interesting problem we ran into in Logisim, was that so in the Logisim simulation here for the memory, what happened was that when we'd go to, I forgot, it's kind of hard to describe, but basically as the clock pulse would change, we'd have so like on the when we were on the low part of it, on the negative part, the address would, the correct address would be sent to the this block of RAM, but it wouldn't actually change until the positive clock edge. So until we went up, like right as we went up, that's when it would trigger and change. But at the same time as that would happen, something else was happening in the CU that basically made it so that the destination for the results that was being loaded from there was being changed then as well, and so it would end up not loading everything correctly. And Ethan fixed this by simply changing the trigger from the rising edge to the falling edge of the clock. So it just had to be slightly out of sync, but that actually fixed it entirely without disrupting anything else. So there was that.
That's precisely why execution phases usually have a bunch of sub-phases, really. So like when you hear of a pipeline with like 40 stages, it's usually got like 35 execution stages, and not all of them are used depending on the instruction. And sometimes you gotta stop, use one edge, then another edge.
Yeah.
Let the signal stabilize. The timing diagrams would show you the signals propagating.
Oop, that's the wrong one. I don't want that. Actually, that's an interesting point. So this was like for the memory reference one. If I can actually open up the this is what the Logisim thing reads.
Yeah.
Logisim reads something like this. It's not like pure binary. It's actually textual, but like if we were doing this in a real case, it'd just be plain binary. It always starts with this header here, and then it's just all in hex, and there's a certain way you're supposed to format this. But that's how it gets read into Logisim.
Yeah, and the memory reference would even need more stages in the pipeline, sub stages really,
Yeah, in practice, yeah, we'd need more to do that.
because you're running at different clock speeds, with your front side bus and your memory and everything. And plus you gotta like do other things, typically error correction, or you gotta like stabilize your address signals on the address line going across the front side bus to the memory and wait and know to wait long enough, and then often the RAM will say, okay, now I've got it. I've got something stabilized on the data bus. And then you say, okay, give it to me. And so, yeah. But
Yeah.
so I mean, you're touching on some really complex, cool things.
Yeah, that's something that'd be more helpful to have timing diagrams and whatnot to actually learn how to do this stuff. So
Yeah,
hopefully in the future we can get that better.
yeah, it's tricky in Logisim, and even in the HDL, it's hard to get the timing out of that.
Mm-hmm.
The whole test bed. That's precisely why I want to find ways of getting those timing diagrams, because you got to slow things down. I mean, you have a ton of complexity here beyond what I would expect from a normal couple labs. But if you're going to make a full-blown processor, then it's critical that you get timing diagrams, because then when you want to push it to its maximum speed, you don't know where the problems are going to be unless you know where all those edges are and they need to be, and how many states, separate states you need, sub-phases in the pipeline to deal with each of them. Yeah, cool.
Yeah, so the last, so we did also end up actually implementing branching and looping in this.
Oh, really? Oh, cool.
Yeah, well, this is an example of, this is actually an infinite loop, and I think this one's actually loaded directly into the program already. This is an infinite loop. So there's an example for how this works. So again, I think I mentioned the addresses for everything in code memory are 16-bit, not 8-bit. This poses a bit of a challenge. So in order to actually set things for the program counter, you have to use more than just the accumulator. So I have to use an accumulator and a register, I think is the way of doing it. So
that makes sense. For your address formation, you're going to need to use 2 8-bits.
Yeah. So here we have we start by setting up the upper byte for the program counter. So you move 0 into the accumulator, and then the accumulator into register 0. And that prepares the upper byte of the PC counter. And then we move the value for the lower byte into the accumulator, which is 0, because we're just going back to the beginning of the program. And then here we have, this is the actual, I didn't label it jump. It probably would have made more sense to actually call this jump, but it's just move for now, because that's what I stuck with. But it will take the accumulator and the register we wanted to use, which was register 0, and it will put them into the lower and upper bytes of the PC register, respectively. And
you remember the DPTR in the 8051 microcontroller? Like, there's a program counter, and that's what's normally used for the normal address range that's in the single chip, But to use external memory, which is going to be bigger, that's probably why you want to go external. The DPTR is more bits, and so you had to do just this kind of thing. Put 2 pieces in there, Yeah.
Yeah, this is interesting.
That's good. It's real. This is a real thing.
Yeah, so here's I can actually just run this. I mean, I'll just put it on like auto run instead of manually clicking through this. So here's let me just make sure everything's reset. Okay, so I think this is running at a clock frequency of 16 hertz. Yep, so I'm going to enable ticks here to run the simulation. And there we go. You can see it over here. It is moving between these. You can see the clock is like freaking out if we're going at 16 hertz. Yeah.
That's cool.
Yeah, you can see it. Now, it was interesting. You'll notice it. If you're not familiar with assembly language that much, what you'll notice here in the computer is that this thing is moving along. For a second, it pops down to this next line. And the reason that's happening is because directly after the fetch phase of the instruction cycle executes, it is actually immediately incrementing the program counter. So it goes to the next one immediately, so it doesn't have to take care of that. It's just part of that phase. But then because that last instruction tells it to change the program counter, it gets changed again. And so that sets it back to this first instruction here.
Yeah, that's good.
Yeah, so we did have conditional versions of all of this. And I could show you that, but I'm probably not going to.
Asking everybody in 230 class to specify exactly why the program counter is a counter and what that has to do with probability. Well, you know, people will balk at the word probability, but it's, you know, because in all probability, you want to go to the next thing, right? It's just,
Yeah.
you know that.
That's an interesting point. Yeah, this was a test with some more jumps, and these will try to skip things. So, like, I'm not going to run this one because it doesn't stop, but like, the idea here is for this first one, we try moving something. This is just another example of the unconditional jump. This will try to move the address 05. Yeah, this will try to move to address 5 in hex. And it succeeds, which is directly after this line here, line 7 in here. So it ends up skipping this one. So you will not, if you run this, you'll notice that after this part goes here, that the accumulator will not be set to the hex value FF because it skips that. So that's a test. This one will set the flags register to all zeros, and then it will try to skip over this last line here. But because this is a conditional jump depending on the carry flag, which is the first bit of the flags register, because it is 0 and therefore not set, it does not jump, and this line is executed. So you do see it get set to this value. And then it's the same thing again here, but this time we set that bit to 1, and it does manage to skip this one. So yeah, that's basically the entirety of what we had.
That's good. You cut off a big piece of work and you made it work. I like it a lot. Nice. Okay. Well,
right, any other questions, or am I done?
Yeah. Anybody have questions? No, that's good.